We will now discuss multiple importance sampling, which is really the final component you need to implement for homework 4 to build a path tracer that is very close to state of the art. Multiple importance sampling goes back to the classic paper by Veach and Giebus in 1995. They introduced this classic scene which has 4 lights of increasing sizes from left to right and 4 materials of increasing glossiness from bottom to top. You consider BRDF importance sampling only, no next event estimation, so no explicit direct lighting or light sampling paths. We'll see that this is mostly noisy, but when you have sharp reflections, especially from wide light sources, this is handled well. You also compare with light sampling, which is next event estimation, which is mostly better, but it is noisy for sharp reflections. The question they asked is, can we combine the BRDF and light next event estimation sampling? Veach's multiple importance sampling provides a way and provides bounds. It is very robust and works well with shiny or rough surfaces. In fact, it is arguably perhaps the most important development in practical implementation of path tracing in the industry and in production rendering. It has been recognized with a very highly prestigious Scientific and Engineering Technical Academy Award. And even today, going back to the last year, there were multiple papers at SIGGRAPH and SIGGRAPH Asia exploring refinements to multiple importance sampling. Here is the example scene with BRDF importance sampling. In general, it's very noisy everywhere. However, if you look at the top right region, which has a near mirror BRDF and wider area light sources, you notice that it is actually handled well. On the other hand, if you do next event estimation for direct lighting, most of the scene is actually handled quite well, but in the top right regions, you cannot actually handle the scene very well because this is a near mirror surface and most directions to the light don't have a significant contribution, so you really want BRDF sampling. If you combine lighting and BRDF sampling using multiple importance sampling, now the entire scene is handled well. We saw that for that scene, multiple importance sampling relied on next event estimation or light source sampling almost everywhere, but it has the ability to rely on BRDF importance sampling when needed. We will follow a multi-sample model where you sample both distributions at each intersection. The general case mathematically for MIS is you have n samples drawn from a variety of different sampling techniques. The way I've written it here is that you have n different sampling techniques, from each of which you draw ni samples. Because you divide by 1 over ni, and you have the function divided by the probability distribution function, this is actually unbiased for each technique, and therefore the sum of the techniques is also unbiased as long as your weight sum functions sum to 1. There is an interesting theory with multiple importance sampling. You are welcome to read the original paper in 1995, but there are also a number of extensions going on to the current day, and you can read some of the most recent papers in 2019. Veach and Giebus proposed the balance and power heuristics that they showed were provably good under certain assumptions. The homework uses the power heuristic with beta is equal to 2. This is very simply defined in this way. The weight of technique I at the direction omega is the probability distribution function of I to the power beta at omega divided by the sum of the probability distribution functions of all of the techniques to the power of beta. Therefore, if one technique has a high probability distribution function value at a given omega, that technique will be preferred to the other techniques. And in this way, you ensure that you use the technique that is most preferred and weight them properly. There is a subtle point here that you need to evaluate the probabilities of all of the techniques in the denominator. Therefore, you need to have a way of evaluating the probability at any given sample direction, not only the sample directions that particular technique provides. Sometimes this can be a slightly tricky issue that you need to bear in mind. This also opens up a natural abstract interface for sampling. We will discuss it in the next segment with respect to an abstract interface for representing BRDFs, but really it can be used with any function, including, for example, the lighting. You define a quantity with this interface. So eval evaluates the quantity at a particular direction. Sample generates samples for this quantity. And PDF generates the probability distribution function at a particular direction. You can now combine these different functions. If you want the value or the estimator, you will take eval and you will divide by the PDF. Sometimes it's preferable to have a separate function for that, which enables you to analytically cancel terms that appear in both the eval and the PDF function. Furthermore, you are given the ability to sample according to that distribution. That's what the sample function does. And you're given the probability distribution function for an arbitrary direction, which is important in being able to apply multiple importance sampling. Let's talk about lighting BRDF sample. For now, you have one sample on the light from next event estimation and one from the BRDF. We already know the probability distribution function from the BRDF. We've just talked about that in the previous segment. We also sampled according to the light, but in fact, these were not in the same space. The light probability distribution function was over the area of the light. So we can't directly combine that with the BRDF function. We have to convert the light probability distribution function to 1 over the angular domain. That can be done by applying this formula, d omega is equal to dA cos theta by r square, or equivalently dA is equal to d omega times r square divided by cosine theta. Therefore, the probability distribution over the area was 1 over A. You have to correct that according to this normalization term. For multiple lights, there is a simple normalization, and you can see the homework for that. You then combine next event estimation and BRDF sampling using the power heuristic, as we discussed before, with beta is equal to 2. Now, the implementation of multiple importance sampling is really the capstone achievement in this course, and it can be tricky. Please see the assignment. Some hints generally to get it working. First, disable next event estimation and just use BRDF sampling for the direct. And then have a separate next event estimation function. So toggle between lighting and BRDF sampling and see if you're able to reproduce the images I showed you earlier for the beach scene. Now you implement the probability distribution function for next event estimation, and there is a little bit of carefulness you need to do to avoid dividing by 0. And finally, you implement the balance heuristic or the weight function, and it's worth also visualizing the weighting for the lighting and the BRDF, which I'll show you on the next slide. And then you can combine them with multiple importance sampling and enable both techniques. See the assignment carefully, and note also that the multiple importance sampling is applied for the direct lighting only. In the beach scene, there is actually no indirect lighting applied. And also note that this assignment involves some level of gamma correction, so read those aspects in the homework. Here are the multiple importance sampling weights. You see that when you're doing BRDF importance sampling on the left, in most places is actually close to 0. But especially towards the top and right of the image, BRDF sampling is preferred, the probability distribution functions are higher, and you're effectively taking most of the information from the BRDF sampling, while the remainder of the image is coming from the next event estimation or the lighting sampling. And by combining them with multiple importance sampling, you can get a high quality image that is robust in cases with complex lighting and BRDF.